Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I'm going back to galaxies yet again, and this time we're going to have a look at peanut galaxies, which sounds a bit bizarre, but the reason is they kind of look a bit like a peanut, hence their name. And we're going to have a look at what might form them, why they kind of look like a peanut. And before I do that, I'm going to have a summary of galaxies. Now, if you've seen some of my other videos about galaxies, I'm just going to give an introduction to what galaxies are. If you're new to my videos or new to galaxies and astrophysics, then I'll just kind of summarize what galaxies are before we go into what a peanut galaxy is. But if you know all of that, then blast through the first part and look at the kind of the end where we talk about the peanut galaxy. So just to summarise really what galaxies are, these are enormous systems of stars, gas, dust, dark matter. They're all held together by gravity. Now there's different sorts, different types, but basically that's what they're mostly made of. Depending on their type, their size, their age, they have different ratios of stars, gas, dust and all that sort of thing, but they're basically made like that, and they're gravitationally bound. So all that stuff's kind of gravitationally bound in these large sort of structures known as galaxies. These are some of the largest structures in the universe, apart from the structures the galaxies themselves make, but that's a whole other topic for another video, like clusters of galaxies and that sort of thing. So lots of different sizes and shapes. These here are mostly disc-like galaxies, but we've got spiral galaxies, lenticular galaxies, elliptical galaxies. So some of them are like discs, some of them are more kind of spherical, more like a ball. Some have got lots of old stars, new stars, young stars, lots of gas. But anyway, a whole different range of sizes and shapes depending on where they are in the evolution, where they are in the universe as well. So the basic types of galaxies we can identify on this kind of the Hubble galaxy classification tuning fork, really. And this is like the classic way to classify them. And it looks like a tuning fork. And on the right hand side, we have our spiral galaxies. Now, it typically normally shows two branches, like the upper branch is normal spirals. They have a more spherical central bulge. The ones along the bottom are barred spirals, a bit like the Milky Way. They have a central bar in the center, which is not spherical. Sometimes you may find that there's actually three of those kind of forks or bits, pathways coming out on the right hand side, and that's because we have ones which don't quite have a full bar, and we have ones that are, they're not quite a perfectly spherical bulge, and they're called intermediate galaxies. So we have ones kind of in between sometimes, and they sit on that side there. They evolve right to left, so their spiral arms get more tightly wound. They lose gas content because they turn it into stars. Basically, the stars age, so they get redder. And then you have your elliptical galaxies, and we classify them purely on shape, not on their age necessarily, but it's how elliptical they are. So it can be from E0 to E7. And I've done a separate video actually on the kind of the E7 side, the more elliptical side, because they might not actually be elliptical galaxies. They're most likely lenticular disc-like galaxies that are viewed a bit more edge on, and we can't really tell because lenticulars don't have spiral arms, so they kind of look a bit like a squashed elliptical. But anyway, elliptical galaxies, old stars, very little to no gas, no recent star formation. They appear quite red, and they're just, they don't have spiral arms, and they're classified purely by their shape. Now, the bit we're interested in for this particular video is the barred spirals. So that bottom branch there on your classification tuning fork is our barred spirals there. They're the ones we're interested in for the peanut galaxies. We'll explain why as we go through. Now, if we kind of look face on at these barred spiral galaxies, they've got a really obvious bar in the center there. It's an elongated structure, whereas the normal spirals, if we're looking at it kind of face on, it would have a more circular, bright central region, but a barred spiral has this more elongated bar in the center, hence their name, barred spiral galaxies. Now, if you view it if you view a spiral disc-like galaxy edge on, the actual disc part is relatively flat, and that's true for barred spirals and your normal spiral galaxies. The disc component, so we're not looking at the central part this time, we're looking at the main disc of the galaxy. They're typically quite flat. So again, they're disc-like. An elliptical galaxy, that's not the case. That's true for your barred and your normal spirals. Now, if we go to any typical disk-like galaxy, spiral galaxy, they have a central bulge. Now in normal spirals, this is quite spherical. So here you're looking kind of edge on actually, and you can see you've got this kind of vertically extended or spherical looking central bright region. If you go further out to the edges, that's your disk, and you can see it gets flatter. So the central part is more vertical, it's more spherical, whereas the disk is flatter. And in this particular disk, in the disk component of a spiral galaxy or disk-like galaxy, the stars are typically orbiting in a common direction. They're kind of orbiting in a common plane, and it creates this flatter structure. Or it doesn't necessarily create it, but one or the other, they're all orbiting relatively in this common plane, which means that they have a fairly flat structure. Basically, the stars are moving in a common direction. Now, if you go to the central region in the central bulge, again, this is for most spirals, the central region, the stars here are moving a bit more randomly, and they have kind of more vertical movement. So they might be going up and down as opposed to just kind of in the plane. And that gives this central region a bit more of a vertical structure. In fact, in these central bulges, the stars are moving more like they would do in an elliptical galaxy. So an elliptical galaxy, the stars have a bit more random motion. They aren't rotating just as much as a disk-like galaxy. And because of that, you get more of a vertical structure. Because the stars could be going in any direction, it means that you get this vertical, spherical sort of structure. Now, in a bar, the stars are taking more elongated orbits. So we're looking face on, stars are a bit more elongated. They're kind of disturbed by gravitational instabilities. The actual galaxy itself over time can kind of put those stars on more elongated orbits. And actually, if we look at the evolution of spiral galaxies, most spiral galaxies will have a bar at some point in their life. So it's something that does typically evolve, and it's down to internal dynamics that causes these elongated orbits. Now, over time, we get these gravitational instabilities which can cause the bar to actually buckle, and that causes more of a vertical sort of structure to it. So it starts to kind of go, or thicker, I suppose is the right way. You've got that thinner disk, and in the central part, those gravitational instabilities cause the bar to buckle, which gives it a bit more of a vertical structure. So it gives a vertical thickening, basically, which kind of extends out further than the disk part of the actual galaxy itself. So what's happening here? Well, again, individual stars are taking orbits kind of out of the plane. They've now got elongated orbits. So they're taking elongated orbits vertically as well as kind of in the bar. So you can start to see, if we overlay all of those sorts of orbits, we actually might end up with in a very interesting sort of shape. So if we were to take those individual stars on those elongated orbits, they've been kind of gravitationally perturbed by the galaxy itself, internal dynamics over a long period of time. And when you overlay them on top of each other, you actually get this kind of peanut-like shape, or actually it can be a boxy or even like an X-like structure. And I'll show you some pictures of some galaxies in a little bit, just to see what you can see kind of as they overlay. Stars are emitting light, so where they're denser, you get that sort of structure. But anyway, you get this sort of peanut sort of structure. So here you've got one, you can kind of see like the X shape there actually. So this is kind of viewed almost edge on. And all peanut galaxies are basically barred spiral galaxies that are viewed edge on. So you're looking edge on at a barred spiral galaxy, and because of those orbits of those stars that are now overlaid onto one another, you get that sort of peanut or X sort of structure in the center part. So again, you've got another one there. Probably can't quite see that very well, but you've got a very faint kind of X sort of structure there emanating out from the center part. Again, we would kind of classify that as a peanut galaxy because it kind of looks a little bit like one. Think of those stars, figure of eight sort of, they're not doing a figure of eight orbit, but it kind of almost maps out when you superimpose them all on each other, which makes that peanut sort of structure. So thank you for watching. If you enjoy the videos or find them helpful, then do consider becoming a member of the channel. Obviously helps support the channel, but there's also extra videos in the members section as well. So thank you for watching.